In this video, I'll take a look at how to work stoichiometric problems, including limiting reactant problems. So the first step to working stoichiometric problems is to balance your equation. So if I have, well, get my pen working. There we go. Okay, if I have sodium nitrate and I add lead oxide to that, I end up with lead 2 nitrate and sodium 2 oxide. Okay, so this is my equation. Move that. The first thing I have to do is determine if this is balanced. Well, I can see right away it's not, because I have 1 sodium over here and I have 2 over here. So the first thing I've got to do is balance my equation. So I'm going to write out my atoms and my polyatomic ions here, and I'm going to count up how many I have on each side. So I have 1 sodium. Now I'm going to keep my polyatomic ion together. Since I have it on both sides, I can keep it together. And I have 1 of those on this side, 1 lead, 1 oxygen. Over here, I see I have 2 sodiums. I have 2 nitrates because of that little subscript there, 1 lead, and 1 oxygen. So really my difference is with my Na and my NO3 here. So what I'm going to have to do is put a 2 right here, which will now give me 2 sodiums and 2 nitrates, because when I put a coefficient, I have to multiply it by each part of the compound. So now my equation is balanced. Okay. If I don't balance my equation ahead of time, then my answer when I work a stoichiometric problem is going to be incorrect. So when I say stoichiometric problems, what I'm talking about is we are given a certain amount of one of our compounds. So let's say I'm given a certain amount of grams of lead oxide, lead 2 oxide. And I'm asked to figure out some other piece of information, like I may be asked how many grams of sodium oxide, or I may be asked how many moles of lead 2 nitrate can be formed, or I may ask how many molecules are formed. So I'm given some starting piece of information and then asked to figure out something else about it. Okay. So let's say that in this equation, so I'm going to rewrite the equation I just had. 2NaNO3 plus lead oxide. All right, so there's my equation. So let's say I'm told that I start with 6.8 grams of lead oxide, and I want to know how much sodium oxide will be produced. So I want to know how many grams of sodium oxide are going to be produced. Now, if you refer to the hands-on stoichiometry handout that's in the course, you see hands, and you see that your moles are in the palms of the hands, and then grams, liters, and the FAM, okay, formula units, atoms, and molecules are on the fingers, okay? So basically what that means is you can't go from fingertip to fingertip without touching the palm first, okay? So let me bring that up and I will show you what I mean. So here is my hands-on stoichiometry handout. And everything connects to the mole. You'll see all these arrows connecting to the mole. So everything has to connect through the mole. So if I'm given grams of lead oxide, I can't go directly to grams of sodium oxide. The first thing I have to do is use my molar mass to get to the mole of A. Then I'll use my mole to mole ratio from my balanced equation to get to my mole of B. And then I'll use my molar mass then to get to grams of B. So I start here with grams of lead oxide. I get my molar mass to tell me how many moles of lead oxide I have. I use my balanced equation to tell me how many moles of sodium oxide I'll have. Then I use my molar mass to finally get to grams of sodium oxide. So if I'm going from grams to grams, it's going to be a 3-step process. 1, 2, 3. So it's best to kind of map out your process before you begin. So I'll show you how to do that. So here we are back at our problem, okay? And I'm always going to start with what I know. And in this case, I know I have 6.8 grams of lead 2 oxide. And I know that it's going to be a 3-step problem. And I know my goal is to get to grams of Na2 oxide. That's my final goal, is to get here. So now I'm going to figure out, what am I going to put in the middle? Okay, so I know my first step here has got to be molar mass, because I've got to get to moles of lead 2 oxide. Now, this is on the top. Grams of lead oxide is on the top here. So grams of lead oxide has to go on the bottom here. And since this is molar mass, I know that that's the amount in 1 mole of lead oxide. Okay, so my grams cancel. And I'm going to get this number right here. I'm going to put a little box here because I'm going to come back to this. This is going to come from my periodic table. Okay, now, since 1 mole of lead oxide is on the top here, I know that that has to be on the bottom here, okay? Because this is going to be my mole to mole ratio here. Since I'm trying to solve for Na2O, I'm going to go to my balanced equation, right? And I see in my balanced equation, I have 1 mole of lead oxide and 1 mole of sodium oxide. If we don't have a coefficient here, then I understand that to be 1. So I have a 1-to-1 ratio, okay? Now my moles of lead oxide will cancel. And then I know my final step is to get back to molar mass over here. So, oops, this should be mole, okay? So I know 1 mole of Na2O has to go here, so it can cancel. And then I'm going to get my grams of sodium oxide from the periodic table, okay? So now I've kind of got my skeleton. All I need to do is go to my periodic table and get my molar masses, okay? So you go to the periodic table and get those. So I've gone to the periodic table now, and I've found my masses for what I need. So lead has a molar mass of 207.2, and oxygen has a molar mass of 16. So when I add those together, I get 223.2. That's what's going to go here. Okay. And then over here, sodium has a molar mass of 22.99, but I have 2 of those. That subscript tells me that. So I'll multiply 22.99 times 2, which will give me 45.98. And then I've got 1 oxygen. So I'm at sodium 45.98, oxygen 16, and that gives me 61.98 grams for my molar mass. So now the last step is multiply across the top, divide across the bottom. So I'm going to say 6.8 times 61.98, and then I'm going to divide that by 223.2. And when I do that, my answer, so how many grams of sodium oxide am I going to have? I'm going to get a different color here. 1.888. Now my last step is to figure out significant figures, okay? So right here in my problem, this is 2 significant digits. So I need 2 sig figs in my answer. So I'm going to round that, and I'm going to say my answer is 1.9 grams of Na2O. So that is my answer, okay? So let's look at another one, okay? So let's say I have, let's do NH3 plus O2 yields NO2 plus H2O. So my first step is to balance my equation. So I'm going to start here and figure out how many I have. So I have 1 nitrogen, 3 hydrogen, and 2 oxygen, 1 nitrogen, 2 hydrogen, and I have to add this 2 plus this 1, so I have 3 oxygen. Now, with 2 and 3 here, my least common multiple is going to be 6. So I want to get to 6. So in order to get to 6, I need to multiply this by 2. So I'm going to have to put a 2 here, which is now going to change both my nitrogen and my hydrogen. So I'll have 2 nitrogen and 6 hydrogen. So over here, I'm going to change my hydrogen. I need to put a 3 here. So that gives me 6, because I've got to multiply it by that subscript. And now that's going to give me 3 oxygen here plus 2 here is 5. But now I've disrupted my nitrogen, so I'm going to put a 2 here. Okay, so now I have 2 nitrogen. And I've got 2 times this 2, so 4. I've got 7 oxygen. Well, I can't, you know, if I look here, 2 and 7, I'm going to end up having to find another multiple of those because 2 won't go into 7. So I'm going to have to put a 7 here, right? And that's going to make this 14. But now what am I going to do? Now I've got to figure out how I'm going to balance these, okay? So I've got to figure out how I can get to 14 oxygen. So I'm going to end up having to change these again. When you have an odd oxygen out here, like when you have O2 here and like water over here, it's always a pain to balance these. And so sometimes it's trial and error. You know, I can't just look at an equation and know exactly how it should be balanced. I have to work through it myself. So now I've got 14 oxygen here. I've got 7 over here. I've got to figure out how I can get to 14. So if I know I need at least 3 hydrogen here to get me balanced over here. And I have 4 here. So what happens if I put, let's say, let's double this to a 6 and see if that will get me closer. So now I'm going to have 12. and I'm going to have 6 oxygen plus 4. I've got 10. So now I need 4 more. So I'm going to change this to a 4. Is that right? Yes. So now I'm going to have 4 nitrogen and 6 plus 8 gives me 14 oxygen. So now I'm going to come back and fix my nitrogen and hydrogen over here. So let's see, if I go 4 here, then that's going to give me 4 nitrogen, 4 times 3, 12 hydrogen. So see, I just had to do a little bit of trial and error to get me to where I'm balanced. So my balanced equation would be 4 NH3 plus 7 O2 yields 4 NO2 plus 6 H2O. So that's going to be my balanced equation. Now, I'm going to work a problem with this. So let me bring up a new thing here. I'm going to rewrite my problem. 4 NH3 plus 7 O2 yields 4 NO2 plus 6 H2O. Okay. Now, on a limiting reactant problem, what that means is that something is going to run out first. You're going to run out of one of your reactants before you run out of the other one. Okay. So and a limiting reactant problem is going to be set up a little bit differently. It's going to be set up something like this. If you combine 72.3 grams of ammonia, which is NH3, with 112 grams of O2, how much NO2 is made? So that's going to be your limiting reactant problem. So they're not going to tell you which one is limiting. You're going to have to figure this out for yourself. And the way that you're going to do that is you essentially have to work out the problem using 72.3 grams of ammonia as well as 112 grams of oxygen, solving for how much NO2 is made. So when I set up my skeletons, it's still going to be a 3-step problem because I'm going from grams to grams. So my grams of NH3 go here, and that's the amount in 1 mole because this is my molar mass. Then I'm going to use my mole to mole ratio. I'm trying to solve for NO2, so I'm going to put moles of NO2 at the top. I need to cancel out moles of NH3, so that goes at the bottom. And then again, I need to cancel out moles of NO2 here, and I'm going to get my molar mass here. So what I need to do now is I need to figure out my molar mass of NH3, go to my balanced equation and get my mole to mole ratio, and then get my molar mass of NO2. So the first thing I'm going to look at here is getting my mole to mole ratio. So I go up here to my balanced equation and I see that I have 4 moles of NO2. So I'm going to put a 4 here, and I have 4 moles of NH3, so I put a 4 here. Now, if your mole to mole ratio is the same on top and bottom, we can cancel that out to be 1, just like you were reducing a fraction. Okay. So now I need to get my molar mass for ammonia, NH3, and my molar mass for NO2. So I'm going to go to the periodic table and get that. Now, I know that my molar mass of nitrogen is 14.01, and hydrogen is 1.01, and I have 3 of those. So when I add that up, I'm going to get 17.04. So that's going to go right here. And then over here, Again, I know nitrogen is 14.01. I've got 2 oxygen, so 16 times 2 is 32. And when I add those together, I get 46.01, and that's going to go here. And then I'm going to multiply across the top and divide across the bottom. So when I do that, I get 72.3 times 46.01 divided by 17.04, and I end up with 195 grams of NO2. Okay, now that's just the first step in my problem. I've figured out if I start with 72.3 grams of ammonia, I get 195 grams of NO2. But I've also got 112 grams of oxygen, so I have to figure out which one is my limiting reactant. So I'm going to erase this so I can make a little bit more room down here and finish working the problem. So I'm going to do the exact same problem, except I'm going to start with 112 grams of oxygen. So I know grams of oxygen goes here, and I'm going to get my molar mass, so that's the amount in 1 mole. I've got to do my mole to mole ratio. I'm going to put moles of O2 on the bottom because that has to cancel, and moles of NO2 on the top because that's what I'm looking for. And then I'm going to get my molar mass of NO2. And so I can just plug in, I've already figured out my molar mass, so I just plug that in, okay? I go to my balanced equation and get my mole to mole ratio. I have 4 moles of NO2, and I see that I have 7 moles of O2. And then the last thing I need here is my molar mass of O2, and I'm going to say 16 times 2 because the mass of 1 oxygen is 16. So now I have it filled in. Now this time I can't reduce because I've got 4/7. So again, I'm going to multiply across the top, 112 times 4 times 46.01. And then I'm going to divide by 32 times 7, which is 224. And I get 92.0, and that's grams of NO2. Now, when I look at my results here, I see if I start with 72.3 grams of ammonia, I get 195 grams of NO2. If I start with 112 grams of O2, I only get 92 grams of NO2. So my oxygen then is the limiting reactant. I'm going to run out of oxygen first. So I can only produce 92.0 grams of NO2. It doesn't matter if I have 1,000 grams of ammonia. If I only have 112 grams of O2, I can only produce 92 grams of NO2. Okay, so this would be a limiting reactant problem where you work the problem out twice using the amounts of both of your reactants. And whichever one is the least is the amount you're going to have, because it says how much NO2 is made. Well, this is how much NO2 is made, 92.0. So you need to, circle that or put a box around it or something so that I know you understand that this is the limiting reactant, that I can't make 195 grams. I can only make 92 grams. So these are limiting reactant problems. And if you have any other questions, you can feel free to let me know.